Welcome to this explainer on the EGU-ARC architecture. Look, today we're diving into a fundamentally uncompromising approach to artificial intelligence. We're not talking about AI that just chatters at you or makes plausible-sounding guesses. No, we're looking at a system deliberately designed to force AI into rigorous, exact, and verifiable logical reasoning. So if you're tired of language models hallucinating their way through complex logic puzzles, you are absolutely in the right place.
Right off the bat, I want to shatter a really common misconception. Check out this quote. Glyphs are not magic. Emojis are not latent space access. There's this popular myth floating around that just throwing emojis into an AI prompt acts as some kind of whimsical hack, right? Like it magically unlocks hidden intelligence. Well, it doesn't. In the EGU-ARC framework, every single symbolic claim absolutely must map to a formally defined semantic object. An emoji? It's literally just a human-readable alias for a strict, unbending mathematical operator.
Okay, let's dive into this. Section 1, the illusion of magic and why we have to reject intuition.
So, standard large language models are, well, famously terrible at visual grid puzzles, like the ARC benchmark. And that's because they rely on sloppy, intuitive guessing. They kind of just glance at a puzzle, rely on what feels right based on their massive training data, and blurt out an answer. EGU-ARC completely rejects that approach. Instead, it uses a formal pipeline. It takes Unicode symbols and pushes them through the strict normalization, lexing, and parsing phase until it becomes a pure machine-readable syntax. There's literally zero room for intuition here.
Basically, this system operates on brutal determinism. Assumptions are completely banned. Just look at these constraints. No fuzzy scoring. Zero visual approximation. And this is key. Color is treated strictly as a symbol. You know, an LLM might see red and automatically assume danger or stop. But EGU-ARC, it sees red simply as color ID 2 until definitive structural evidence proves it actually serves a specific role, like a boundary or a target. You also can't just derive a rule from a single example if alternatives exist. It is completely uncompromising.
Moving on to Section 2, Anatomy of Glyph Block IR. Think of this as the factory line.
Now, what's really interesting about this slide is that to truly understand EGU-ARC, you kind of have to treat it like a high-tech factory assembly line. Every single piece of information has to pass through Glyph Block IR, the intermediate representation. Remember those whimsical emojis we were just talking about? They actually lock into a rigid, deterministically serializable JSON structure here. This IR is the bridge. It translates human-readable glyphs into a format that the machine can formally verify without any ambiguity whatsoever. It essentially ensures the AI's thoughts are strictly typed and structurally sound.
And that brings us right to the architectural flow. Notice how separated these components actually are. You've got the ARC task JSON flowing to the runtime, then into the Glyph Block IR, and finally to verification. The absolutely crucial detail to grasp here is that the task itself is never, ever hard-coded into the runtime. This separation is our first major defense against the AI just overfitting or memorizing a specific puzzle. The system is forced to actually learn the rule, not just regurgitate an answer.
Which leads us to Section 3, the epistemic reasoning cycle, functioning as a governed state machine. And this brilliantly illustrates exactly how the V1.1 and V1.2 epistemic reasoning cycle works. We're moving completely away from simple prompt chains and into a governed computational state machine. This cycle physically prevents the AI from skipping straight from seeing a symbol to just throwing out an unverified answer. First, the system has to observe the raw data. Then, it abstracts the objects and relations. From there, it generates a hypothesis, tests that hypothesis against the training examples, and only if it passes perfectly does it reach verify. If a guardrail isn't met, say the prediction doesn't perfectly match the ground truth, the state machine just halts. It forces the system to stop and rethink. Just look at the contrast here. You have the arrogance of a standard LLM blindly claiming, oh, it's obviously a 3x3 palette, without actually proving a thing. But contrast that with EGU-ARC, which structurally tracks the logic. It sets up hypothesis 0, 1, tests it against training example 0, registers a fail, and immediately updates the status to rejected. It's not out here generating persuasive text. It is mathematically proving exactly why a rule does or doesn't work.
To actually find these rules, the architecture relies on what's called the difference engine. Instead of just vaguely describing what the final visible result looks like, the system mathematically computes the exact delta, the true difference, between the input grid and the output grid. It's asking the hard questions: what actually changed? What stayed exactly the same? By isolating those invariant structures, the parts that didn't change at all, the system can pinpoint the precise causal operator, rather than just getting distracted by flashy visuals.
All right, Section 4, the hypothesis tournament. Time for the adversarial search.
So what happens when the system actually finds a rule that works? Or better yet, and think about this for a second, what if multiple hypotheses fit the training data perfectly? A standard AI would just grab the very first one it stumbled upon, run with it, and cross its fingers hoping it generalizes to the test case. But EGU-ARC knows better. It knows that just because a rule works on the training data doesn't mean it's the true underlying rule. It demands an adversarial counter-hypothesis search to find the minimum counterexample. We absolutely need a strict tie-breaking mechanism here.
So the crucial point is the minimum description principle. When multiple rules fit perfectly, the system mathematically favors the simplest executable transformation. What does that mean for us? It means the winning rule is going to have fewer operations, fewer special case exceptions, fewer parameters, and zero unjustified assumptions. It conceptually minimizes rule length while strictly requiring an exact training fit. At the end of the day, the simplest verified truth wins the tournament.
Which brings us to the final hurdle, Section 5, double execution and verification.
Once a hypothesis actually wins that tournament, we enter the final and frankly unforgiving stage of the factory assembly line. This is where we ensure no transcription or implementation errors manage to slip through. The first half of this test is execution A. This is simply the forward application of the winning hypothesis. The system takes that selected rule, directly applies it to the test grid, and steps through the logic to generate an output. Now, this is how most normal systems operate, but as we know, EGU-ARC doesn't stop here.
Let's move to the second phase and see how this builds. This is execution B. In this step, the system takes a completely independent path. It rebuilds the entire rule from scratch, using only the formal typed abstract syntax tree, or AST, of the symbolic description. It's essentially reconstructing the program blind, without looking at the logic from execution A at all, and then it runs that reconstructed program against the test grid.
And that brings us to the brutal acceptance criteria. Execution A must perfectly equal execution B. If these two entirely independent executions do not match exactly, the system immediately registers an execution conflict. It just throws out the result, marks the status as invalid, and the entire system is forced to backtrack and rebuild its logic from the ground up. It's a completely self-policing, incredibly rigorous mechanism.
I really want to highlight this fundamental law of the EGU-ARC specification. Exact means exact. No fuzzy scoring, no semantic similarity. A hypothesis does not achieve that coveted, verified execution status by being close enough. Honestly, if even one single cell in a grid is off by a single coordinate, the entire hypothesis fails. It demands absolute perfection.
So I'm going to leave you at this to think about. If we stop asking AI what a grid looks like based on some blurry latent space intuition, and instead start demanding that it formally prove what structure remains invariant using governed epistemic reasoning, what else can it solve? Think about it. If we can force AI to be mathematically accountable to the evidence, the ceiling for artificial generalization completely changes. Thanks so much for joining me for this explainer, and remember, keep questioning the magic.